All right. Today we would like to talk about next common structure for DAG that is called charge redistribution. Yeah. Anyway, or charge sharing. You can see this for such kind of structure. We use switched capacitor, switch and capacitor. Yeah. For the main idea. After equilibrium, you can see that in theory there won't be any kind of steady current after fully charged or something. So this is very good for low power application. But the problem is low power always means low speed. Okay, so low speed but low power. Yeah, that is a key idea. But before I can tell you the theory, I hope from the very beginning you need to know the simple idea called charge sharing. This is a very good explanation for such kind of concept. Here you can see in this plot we have two kind of capacitors. First of all, C1. It doesn't be switched, and C2 it can be switched. That's it. So from the very beginning, we need to reset the charges between C1 and C2. So we close here, we close there. All those, never mind VA or the others, all of them are shorted to the ground. So after reset, no charge will be stored on both C1 and C2. And after that, we go to the real operation. But before real operation, we need to open it. Okay? And then we switch S2 from ground to V reference. So after such kind of switching, you can see, yeah, some of the current will flow through C2 all the way to C1, right? So right now, how much voltage you can get for node A? Yeah, very simple, right? You can see, according to voltage division, we need to know the impedance. Okay, so if you have G1 and G2, then piece of cake. Everybody knows G1 plus need to over what? G1, right? But now the impedance is 1 over SC. So G1 is 1 over SC1, G2 1 over SC2. So after simplification, finally you get this. Okay? Yeah. But anyway, even you get such kind of very simple equation, I don't think it is helpful enough. So I help you to do further. Yeah. In explanation, the output voltage will be equivalent to your reference voltage by what? By this term. Here, C2 means what? The capacitor will be switched from ground to V reference. Okay? And C total means what? Never mind, it is switched or not. All those capacitance need to be considered, put here. Okay? Got it? Very simple idea. Okay, let's go further. With such kind of very simple idea, we can go for the complete circuit, very complicated complete circuit. Here, you can see this is the charge sharing with minorly weighted capacitors. Okay, in theory, it means you can see 1C, 1C, and then 2C, 4C, all the way. Yeah. The first actually we call it a dummy capacitor. Yeah. Later you will know why. Okay. And then you can see, yeah, 2 to 0th power, 2 to 1st power, 2 to 2nd power, blah blah, all the way. Okay. It means for each bit, the capacitance is doubled. Okay. So we call it minorly weighted. And then the operation is quite similar to this one. Okay, but you say, hey, we have so many capacitors. Oh, who cares? Come here. Again, before each conversion, you need to reset all the capacitors. But how? Ah, very easy, right? You just close all the switches to ground, okay, to reset all the capacitors without any charge, okay? And then, next step, before real operation, this one needs to be opened first, okay? And then, for all those capacitors with the corresponding control bit, if it is 1, it means what? The switch will be changed from ground to reference. Got it? And then, if the control bit is 0, it means nothing happened. That's it. The switch will be steered to the ground. That's it. Okay? So, what will be the result? For node A, how much VA will you get? It looks very simple. It looks very complicated. But if you go back here, what I told you, we have only 2 kinds of capacitors. Okay, one is switched here. The other one, it won't be switched. But C total means I don't care. Every capacitor needs to be counted. Never mind it is switched or not. Okay, so you can see after switching, for all those capacitors with control bit 1, all those will be switched to V reference, right? Because, for example, oh, I'm switched. You are also switched. Oh, switched. Congratulations. All those capacitors are connected in parallel. Why? Because they have the same node A, right? And to the other terminal, oh, all of them are connected to V reference, right? So all of them are connected in parallel, so equivalent to what? C2, right? And for all those with control bit 0, they never be switched. Okay, but they are still connected in parallel because, again, they have node A as one terminal, and the other terminal is what? Is ground. So all of them equivalent to C1. So first of all, what is this? C total. You need to count everybody. I don't care. You will be switched or not. So all of them, right? I don't care. You will be switched or not. So it means all those capacitance needs to be counted. Okay, so C plus C plus. Why you need to have this? If you don't have this dummy C, then you will have only 1C, 2C, 4C all the way to here, right? So if you sum them up, you will get. Are you happy with this? No. Right? So we need to have dummy C, actual C to cancel this, to make the total number. Beautiful. 2 to n's power by C. Bingo. So this is for C total. If you ask me, how about C2? I told you already. For all those capacitors, be switched to V reference. But as I told you, if the control bit is 1, then the capacitor will be counted here. So what is the total C2? Very easy. This one. Why? If this is 1, then this will be counted. Okay? If this is 0, it won't be counted. Right? That's it. So for all those transistors, for all those capacitors, switch to V reference equivalent to this. Simply because if the control bit is 1, it will be counted. If it is 0, it won't be counted. Very, very simple. Okay? So the final result will look like this. And according to 2 to ns power configurations, you can see the first dominant 50% of all the voltage here. Right? Because it is 2 to n minus 1 power, okay, divided 2 to nth power, so it get this one. And how about the second one? Here. So it got this, and all the way. So this is MSB all the way to LSB. Congratulations. If you understand what I'm talking about, the simplest one, it will be very easy for you to understand the most complicated one. But anyway, they have the same idea. They have the same theory. Okay? So, since it's right now, it is really easy to understand what will be go wrong. What will go wrong? What will be the problem? The problem is, to be honest, 1 to 1 to 2 to 4 all the way 2 to n minus 1's power, actually it is really hard to match all of them. All right? If you have such kind of structure, usually the number of bits had a better bit. Only 10, the largest. Okay? And also you need to do very good layout. You need to have very good layout pattern to match all of them. Yeah. I think I showed this in analog IC layout. Anyway, not a big deal, right? To my memory, you need to have such kind 1C and 1C. I mean this one, that one, and then how about 2C? How about 4C? Blah blah blah. Okay. Yeah. Anyway, but for MSB bits, actually, they need to be split, be split into 2 halves. Yeah. For example, if you have anyway, n equals 7, and here 2 to 6 power. So totally for MSB, you have 64C, right? So divided by 2, yeah, the first half here, 32C, and the other half there to the other part. Okay, that is for MSB. For all those MSB, you need to split them into 2 halves. That's it. Okay, yeah. The next problem is, we know that for all those capacitors, they have parasitics. And can you switch CP? No way. You have no way to switch CP, right? So what is the impact of CP? What is the impact of CP? According to this one. Right, again, here, for all those capacitors can be switched. Can CP be switched? No. So, it will be counted to C total. Okay? It means what? You still get this, but you need to be careful. Here, you need to count CP. So what's the result? You still have very good minorly weighted structure to your result. But the problem is it has some kind of gain error, right? Because C total becomes larger than before. C equivalent, the same, all right? So VA will be reduced by CP. That's it. Okay? And then the next question is how to reduce the gain error. Yeah, in brief, how to reduce CP. You may think, oh, piece of cake, I increase all of them, right? So it means C total equals 2 to nth power C plus CP, right? So if I increase this, then the impact of CP will be reduced. Is it true? No. Why not? If you increase, so what is the cause of CP? According to your capacitance. All right? Since you have those capacitance, you have CP. If you increase those capacitance, then CP will also be increased. All right? So never how much you increase the capacitance, the capacitors, CP will be increased proportionally. So it means what? You still get the same gain error. Wow. Okay? Okay? So the only way I can help is, first of all, you can have some kind of capacitors with less CP. For example, we have MIM, right? We have MUM. Okay? This is horizontal parallel plate. Okay? And what is MUM? It stands up. It is vertical. With vertical structure, CP will be reduced very much. Okay? So you can use such kind of MUM structure. If not, if you still have such kind of MIM, okay, horizontal plate instead of vertical plate, then this should be VA instead of that. Okay? Bottom plate, you have top plate, bottom plate. You need to apply bottom plate to be switchable. Don't switch your top plate. Why? You can do your layout and check. If you switch bottom plate, you will get less CP. If you switch that one, you will get larger CP between this and your ground. Okay, that's it. Then we go for the next version of such kind of charge sharing structure with unit capacitor. Yeah, the major benefit is, everybody get the same 1C. Okay? It means what? You can guarantee monotonicity because, for example, right now you have, okay. Anyway, the operation principle is quite easy, right? Yeah, from the beginning you have 0, so everybody won't be switched. You have 0 to the output in theory. What is the next? Next is 1, right? It means what? Only one capacitor will be switched to V reference. All the others were still connected to ground. Okay? So it means from 0 to 1, 1 to 2, 2 to 3, all the way. If you increase your input by 1, it means one more unit capacitor will be switched to V reference. Okay? It can guarantee monotonicity because the more input means the more capacitance be switched to V reference. And according to this one, it means the more C2 here, definitely you will get the more V out. That's it. Okay? So you can promise the more digital input, the more analog output, the more voltage output. You can guarantee such kind of monotonicity. Yeah, but what is the price you need to pay it means you need to have such kind of address decoder. Okay, for example, 8-bit as your input, manual input, then you need to have 2 to 8 power minus 1. So totally, you have 255 output to control all those capacitors. Okay, that's it. But don't be silly. Even though I have only 255 control bit, but pay attention to this. You still have one dummy capacitor. So the total number is still, okay, that's it. One is not switchable. Yeah. The other one structure, we call it MDEC. M means what? Multiplier. 乘法器. Okay? Yeah. So it is not only DEC, but with multiplication. But how to do it? Okay. How to do multiplication? Wow. It's a very simple idea for switched capacitor. For example, if you would like to double the output voltage, what you can do? For example, you have 2C here and 1C there. Okay, that's it. But how to double the voltage? For all those 2C, after they were charged, okay, then you discharge all the charges to the other one. You pour your charges all into one. You have 2C. There is only 1C. Because Q equals CV, right? Okay, so the more charges for this one, the more output voltage. That's it. Okay, that is a very simple idea to do multiplication with switched capacitors. All right, that's it. So how to multiply the input to output by 4? 4 capacitor here, 1 capacitor there. Okay, that's it. Yeah, so it means what? MDEC is really important in maybe pipeline ADC, to my memory. Anyway, you need not only DEC, you need also multiplication. Yeah, anyway. So the main capacitor array here is for this one or for that one. Manually rated or unit capacitor, I don't care. All right? But how to do multiplication? Some capacitor need to be connected here. Okay? That's it. So after you do all the switch, all the necessary switching, then pour POUR down. Pour all the charges into the output capacitor. That's it. So this is the switching sequence for you. Okay? If you would like to design such kind of MDEC, all right, follow the table. You can make it. Again, feedback means what? Some capacitor needs to put here. That's it. All right? And then, we are intelligent humankind. We have a lot of intelligence. What's the problem you will get if the number of bits becomes too much? For example, 13 bits. So all the way from 1C all the way to what? 2 to 12th power. Okay. It means what? The largest capacitor needs to be 4,000 more times than the smallest one. How can you match them? Norway, I told you already. Okay, the best till now is only 10 bits. So beyond 10 bits, forget about it. Your RNL, integral nonlinearity, will become really, really bad. Okay? So what we can do is, through the help of attenuation, you need to be very careful according to attenuation, 衰减. Okay? So the main idea is this one. But, sorry, the order of LSB and MSB is reversed. Right now to the left for LSB, to the right for MSB. Okay? Why? Oh, simply because all those slides are from different professors. All right? I have no time to replot it. Sorry for that. So please accept it. LSB right now here, MSB there. Okay? Let's focus on MSB first. See? Right now, we have 7 bits for MSB here. So 6 bits for LSB. Okay? But it's not important. The important idea is this one for attenuation. Okay, if you look at MSB, you can see from MSB to LSB, from the largest 64, 32, all the way to 1P. Okay? And then, what is next? It should be in practice. Okay? Just like what you write, that is the dot. Okay? What do I mean? If I told you in decimal, 十进位, right? They are integer and to the right, yeah, less than 1. Okay? Anyway, that is what you know. But how about the manually weighted structure? We still have something like that. For example, 1, 0, 1, 1.01, blah, blah, blah. Okay? All those are integers. So you have 2 to 0's power here. Second power, first power, second power, third power, right? But to the right, you have 2 to minus 1, 2 to minus 2, all the way. Okay? So the dot, 小数点, is here. Okay? But sorry for that, MSB here, LSB there. So to the left, this should be 2 to minus 1. That 2 to minus 2, all the way to the minimum. Okay, got it? It means what? Because here you have 32. But equivalently, it needs to be only 1/2, right? So it means what? The attenuation needs to be 64. Right? That's it. That's it. But how to make it for such kind of attenuation? Later I will show. Okay? So if the attenuation is 64, oh, congratulations! For what? Because all those will be divided by 64. Right? Right? That's it. So 32 by 64, you got 2 to minus 1's power. And how about this one? By 64. Oh, it becomes 1/4. Congratulations. It is 2 to minus 2 power. So to the others, piece of cake. Yeah. You can think about it by yourself. You can derive it by yourself. That's it. Anyway, totally, how much capacitance is here? You still have one dummy capacitor here, right? So 1 plus 1 all the way to plus 32. What do you get? 64p, right? Divided by 64. Congratulations. Equivalently, you have 1 picole, just like this, right? So the structure is still very beautiful. Even from MSB, 64, 32, all the way to 1P, 1C here, right? So to the left, you still have another 1C for dummy. Okay? The structure is exactly the same, except for this one. CA means what? The capacitor for you to get attenuation. That's it. Okay? Anyway, so the idea is, if you look at to the left, I told you already, you need to get another 1C. Okay? Equivalently, all of them plus this should equal to 1P. That's it. Okay? So again, according to impedance, the impedance means impedance of CA plus impedance of all of them. All of them 64P. So how much you need to have this? Okay. Again, impedance for capacitor means, right, 1 over SC. Right? So this is 1 over SCA, and that is 1 over 64, blah, blah, blah. All of them together needs to be 1P. So after very simple mathematical calculation, congratulations, you get this. The attenuation capacitor is only 1 point, blah, blah, blah. Okay? That's it. That is the power of attenuation. And right now, you can see the largest capacitor is only 64 instead of 4,000 something. Okay? First of all, you reduce the capacitor size. No. You reduce the chip size, the chip area. You save a lot of money, but you still get even more bits. Does it make any sense? Usually not. Why? The linearity error will be much worse than before. Okay? That is what you need to face. Yeah. With such kind of structure, again, you save area, you save money. Can you enhance the linearity? Usually not. Okay? That is the price you need to pay. Yeah. Anyway, the other problem is it possible for you to make your attenuation capacitor with 1.016, bro? Okay, it is impossible. It is impossible. Okay? Unless after fabrication you have something to fine-tune CA, otherwise forget about it. Okay? My recommendation is never use this one, because it is impossible for you to match CA to all the others. All right? So what you can do is you still use 1P instead of this. Okay? So what is the problem? If you replace the original 1.016 with only 1 pico, you will have some kind of attenuation error. Okay? Yeah. But for how much? See? The error is 1.6%. So it means what? You cannot have too many bits for your LSB. That's it. Otherwise, you will cause too much INL, according to 1.6% in attenuation error. Okay? That's it. So finally, the real structure for you to implement is still 1C here. 1 pico, sorry, 1 pico. Yeah, 1C, the same. Okay? So you have 64, 32 all the way to 1P, and then 1P, and then again 32, 16 all the way to 1P, 1P. That's it. Okay? Yeah. Our intelligence is beyond any kind of imagination. Okay? Please train yourself. If you are the one to create such kind of attenuation idea, perfect. You can apply for such kind of patent. Yeah, and many of the analog IC design houses need to pay you, okay, if they would like to adopt such kind of idea to reduce the overall chip area for money saving. All right? They save money, so they need to pay you. But for real implementation, again, you need to focus on matching. Okay, otherwise you will get a lot of mismatch. Okay? And then if we go further, you can see, hey, you have this idea, so we can apply such kind of attenuation again, and again. So this one, haha, that's it. Okay, from MSB attenuation, the second MSB attenuation all the way to LSB. Okay, so that is the maximum attenuation structure you can have for capacitors, and we call it C to C ladder. You have only one C, two C, one C, two C. Whoa. Okay? Okay? But I need to warn you. With only one attenuation capacitor, you get trouble enough. Okay? You get enough trouble. How about this one? Usually, we don't apply such kind of C to C structure. Why? Because after equilibrium, there isn't any DC path for you. If there's any kind of noise error accumulated here, over there, in between, okay, there isn't any DC path for you to dissipate such kind of error or noise. Okay? 在中间的这些点哈，如果你操作出了问题，有杂讯有错误，没有任何的直流路径可以帮你放电，你要倒大霉。Okay? And this is the reason why we don't. That is only for idea, but in practice, almost nobody adopts such kind of structure. Sorry for that. But you will say, hey, we have R2R. Oh, congratulations. If all those are resistance, no worries. Why? Because resistor will provide such kind of DC path for you to dissipate all the error, all the noise here. Okay, so we have R2R in practice, but we don't have C2C in practice. Only in idea. Yeah, you can talk about this only for fun, but don't do it. Okay? All right? Again, you say, hey, look, I can provide some kind of switches, right? Yeah, to short all those nodes to ground, to do reset before operation. Congratulations. Yeah, you can make it, but still in theory, not in practice. Why? Because how can you implement such kind of switches? Transistor, right? But what is the problem about transistors? The capacitance look like this. It's highly nonlinear. Okay, so if you have switches here, switches there, you will get such kind of highly nonlinear parasitic capacitance to destroy all the performance. Okay, and we say, hey, all right, I know it. So how to solve the problem? Again, for the switches, I mean most switch, right? You can reduce it very much. You can make it as small as possible. Then the parasitic capacitance can be reduced. The nonlinearity can be reduced, right? Bingo, you make it. But again, in theory. How about in practice? The smaller switch you have, then it means what? You need to wait for a much longer time. That's it. Okay? It still doesn't make any sense. So in practice, almost nobody adopts such kind of structure. Okay? That's it. Yeah. Right now we have C array and R array, right? Yeah. Resistor array, R string, and capacitor array, blah, blah, blah. So this is something for you to refer with R array, that is the power consumption. Somebody help me to do such kind of calculation, not myself. And for C array, that is the power. If you divide PR over PC, you have this one. What does it mean? For more than 5 bits, okay, the R array will have larger power dissipation than C array. Okay. Do you have any kind of deck with less than 5 bits? Usually not. Only for very high frequency operation. So this is the reason why people always say capacitor array is more power saving than the others. That's it. Okay? Yeah, but for how much? Yeah, usually 4 to 5 bits more. Okay? And then we are from democratic countries. Yeah, we are not communists. Okay? So we have any kind of freedom. Yeah. If our laws don't say no, then you can do it. Unless our laws say, hey, you cannot do it, then forget about it. Okay? What I would like to say is we have R string, we have capacitor array, but you can still hybrid both of them. Oh, this is a very good idea for you. So for R string, in this structure, we have that for MSBs. Okay, so you have many kind of switches. Yeah. According to your MSB, right? So you can see, if MSB is 0, so you touch those 2 points. Okay? And next one, MSB is 1. Right now, it has 4 MSB, so 2 to 4th power. Yeah, totally. Yeah. 16 levels. 0 here, 1 there. Oh, it is reversed. Okay? Yeah. And then the second, the third, the fourth. Okay, yeah. I told you such kind of flipping. Okay? From the largest to smallest, and then from the smallest to the largest, blah, blah, blah. Oh, you need to be very careful. Otherwise, the switches here needs to be doubled. It doesn't make any sense. We need to reduce the complexity. So usually we have such kind of structure. Okay, but according to your LSB, from largest to smallest, from smallest to largest. Okay? Anyway, I mentioned in previous class. So after that, we have capacitor array. Yeah. After you select according to MSB, for example, you select this one, okay, and that one, yeah, to this structure, okay. We select 2 voltages for LSB capacitor array to do further what? Voltage division by this one. Okay, you select 2 out of all those. Right now we have 16. You select one of them. Yeah, the highest, not the highest, okay, yeah. The maximum, the minimum for next to do further voltage division. Yeah, that's it. That is for the fine structure. So the beauty of the structure is because after equilibrium, if you look from R string to capacitor array after equilibrium, because you don't need, equilibrium means DC, right? So all of them are open circuit. So from resistor string, if you look from R string to capacitor array, all those are open circuit. And this is the reason why we don't need any kind of operation amplifier for isolation. No, you don't need. Okay? Wow, bingo! That is really beautiful. But the price you need to pay is you need to wait for a long enough time for all those charges, all those voltages to be stabilized. according to RC, right? You have resistor here, you have capacitor there. Okay, so how much time you need to wait? You need to be very careful to calculate it. And again, for the worst case, because your time constant means 1 over RC, the largest R will dominate your delay. Okay, and where will be the largest resistance? In the middle. Okay, got it? In the middle. All right, and how about C? All of them. The summation of all those. So you can guess, with such kind of RC hybrid structure, yeah, it's really beautiful. It makes sense. Oh, here for MSB, therefore, you simply combine both structure from 2 to 1. You combine 2 structure into 1. R string for MSB, capacitor array for LSB. That's it. Okay? But the price is the operation speed is much slower than before. According to such kind of R and the C, you need to wait for a much longer time. Okay? Again, it proves what? Nothing is free. Okay? You need to pay for it. In analog IC design, that is your usual case. You get some kind of benefit, advantages, then you need to pay something. Okay? That is the usual case. I'm not talking about the always case, no. But usually, you need to pay something for something. Okay? Usually, you cannot pay nothing for something. No. If you can pay nothing for something, you are Einstein in this field. I'm not. Okay? Yeah. Anyway. Yeah. That is the price. Okay. So next step is, hey, here R string for MSB, there capacitor array for LSB, right? We can swap the structure. Like this. Okay? Capacitor array for MSB and R string for what? LSB, that's it. Okay? The same idea. Just do it by yourself. And then we can go for the final structure. But that is the fattest structure. Current steering. Okay? That's it. Current steering deck, that is the highest speed for highest speed operation, but nothing is free. You need to pay power. Okay? This structure provides you the most speed, but again, it consumes the most power than all the others. All right? And I show you this plot already from the best wired communication IC design house on earth. You can see for such kind of the same number of bits for DAC, according to 0.5, 0.35, 0.25, all the way you can see the process is scaled down. The chip size is scaled down. Congratulations. Okay, but I told you already, the story is totally different for ADC. Yeah, with the same number of bits, even from Broadcom, the chip size is almost the same. You cannot see any scaling down for such kind of process evolution. No. All right, that is really upset. All right, that is the simplest structure for you to refer because you learn it from microelectronics already. Yeah, you can see again from MSB to LSB. Why? Because MSB with the smallest resistance. It means this is AC grounded, not DC. Okay, forget about it. That is AC. All right. So you have, if it is switched to 1, okay, this is for 0. If it is 1, then V reference will be connected to this R, right? Then the current will flow to the other one. Okay, yeah. I explained the idea for you already. Okay, so you can see from MSB to LSB, what is the difference? MSB get R, next to R, then 4R. The current flows into the resistor will be reduced by 2, by another 2 all the way from MSB to LSB. That's a blah, blah, blah. Okay, that is a very simple idea. Yeah, but what is the problem for such kind of structure? You can see the current is either switched off or on. It is really harmful for real operation. To switch your current from 0 to 1, okay, first of all, it will slow down your operation. Second, it will generate a lot of noise. To turn the current on, to turn the current off, wow, forget about it. So this is only functional in idea, not in practice. In practice, no, this is really bad structure. Okay, but what you can do? Okay, again, we are intelligent humankind, so use your eyes as camera. Okay, next. Oh, what is the difference? Huh? Almost the same structure, right? You see, if I go back, that is the original idea in theory. But in practice, we make it here. What is the difference? The order of the switch. It is here. Original. It is to the top, close to V reference, right? But right now, close to ground. Okay? What is the difference? Allow me to highlight the crazy idea for you here. You can see the current is never been turned off. It is either connected to your output or to another ground. Okay? So it means what? Again, the current is always flowing. It never be cut off. It is either directed to the left or directed to the right, but it never be cut off. And then for the switches here, I don't care the direction, because the voltage is to the left, AC grounded. To the right, it's still grounded. Congratulations. For the switch, the operation voltage is exactly the same. No voltage switching. Okay? If you get previous structure, it needs to switch between 0 and V reference. You have voltage switching, it generates a lot of noise and slow down the operation. Right now, after we change the order of your switches with the same structure, okay, we made it. No voltage switching. And the current is never be cut off. Oh, bingo! That is a very good example. We pay nothing for something. Is it correct? Is it correct? This is your free lunch. It means you get such kind of very good benefit. Yeah. No voltage switching. No switching noise. Right? With as fast operation as possible. Oh, yeah. But what is the price? Any price? Any price you need to pay for this? Any price? Sure. What kind of price? Power. Why? Okay. Here, if you don't need it, you can cut it off. The current. Right? Right? Because it's connected to the right, to the left, sorry. 0 and 0. No current here, right? But here, the current is always flowing. Okay? Either to the left or to the right. The current here flows always. So that is the price you need to pay. To get higher speed, you need to consume more power. Okay, got it? But again, we are intelligent humankind. We wouldn't like to waste the power here. Okay, so this is to your positive output. We have the same structure to the left to be your negative output. That's it. You can provide the so-called differential output instead of a single-ended output. Got it? For all the currents, I told you already, because all the current are flowing, never mind to the left or to the right. So the total current through V out plus and VO minus is exactly the same. Okay? Because the current are either to the left, I mean to the minus output, or to the right, to the positive output. Okay? So the total current are fixed. Is fixed. All the currents, either to the left or to the right. So what do I mean? If you get more positive output, it means what? Less negative output. That's it. Okay? This one higher, that one lower, that one higher, this one lower. Congratulations, they are fully differential. That's it. Okay? All right? So with fully differential operation, the power actually is not wasted. I mean to the left. No. It will provide you negative output to provide the so-called fully differential operation. Bingo. And then we go to R2R later. I told you already, C to C. No. That is no good in practice. Okay, but R2R is still functional in practice. Okay? You learned it already from your microelectronics, but allow me to highlight again the simplest idea for such kind of operation. MSB here, okay, and LSB to the right. Sorry for the order. Sometimes to the left LSB, but sometimes to the left MSB. Okay, yeah. Just pay attention to that. Okay, from LSB, you have 2R here. The other 2R there, right? So never mind, the switch is to the left or to the right. To the left, 0. To the right, it's still 0, right? Right? AC grounded. So these 2R and that 2R, actually, they are in parallel. Why? Because we have the same node here. And how about the other node? You are grounded. Me is also grounded. Never mind to the left ground or to the right virtual ground. The same. Okay? So in theory, 2R, this 2R and that 2R are in parallel. Okay, since they are equivalently connected in parallel, so it means what? The current here will be splitted 50%. Okay, you got one half. I get the other half. That's it. And then, since they are connected in parallel, so 2R in parallel with 2R. Bingo, you get only 1R, right? And this 1R and that 1R, oh, you get over 2R. Overall, you get 2R. And 2R and 2R, oh, they are again in parallel. So you got 50%, I got another 50%. Oh, okay. Bingo. So you can see 50% here, 50% there, right? So the current are equivalent, right? And then 50% here, 50% there. It means what? This and that, I am your 50%. Because this current and that current are the same. And this current is split into two halves. So I am 50% of you, but you are the same with that. So I am your 50%, okay? And you are previous one, again 50%. All the way. Right? So, I am your 50%. On the contrary, if I am 1, then you are 2. And again, the other 4, all the way to MSB. That's it. Bingo. That is the so-called R2R, right? So, with such kind of very simple structure, for each bit, you have 1 2R, and the other 1R. That is for MSB. And next bit, 2R and 1R. Everybody 2R and 1R, 2R and 1R, that's it. Only to the final one, you have dummy 2R. That's it. Okay? All right, bingo. Oh, congratulations. But what is the problem? The problem is, in the past, engineers didn't pay good enough attention to the area of such kind of resistors. Usually we say, hey, for R9 and 2R, wow, I need to match them, right? So you have 1R here and 2R there. Oh, congratulations. And then, if they do good enough layout pattern for 1 bit, usually the engineers will apply the same layout from MSB to LSB. Everybody, because again, in theory, everybody get 1 2R and 1 1R. Okay? So after I do a very good, very excellent layout pattern for 1R and 2R, then I duplicate the same layout for all the others. Right? That is the usual case. Not only in the past, even in the class, I think most of the students will do the same silly thing. But what is the problem? The problem is, with the same area, according to Pilgrim's model, after fabrication, the variation, the standard variation, yeah, is reversely proportional to the square root of the device area. It means what? The more area, the less variation after fabrication. Okay? But the problem is, right now, all of you have the same area, so it means even MSB get the same variation as LSB. It doesn't make any sense because MSB is much more important than LSB. Okay? For example, with the same area, you get 1% error, 1% of variation for your LSB. Oh, good enough. Why? Because for INL, everybody knows it should be, hopefully in theory, in practice, less than half LSB. But here is LSB. Half LSB means 50%. Oh, very good. I have only 1% error in your LSB. Good enough, right? More than good enough. But the problem is not here. The problem is there. Because you have the same chip area, okay? So you get the same deviation. You get the same variation after fabrication. Okay, right now if you have 8 bits, right? So LSB 2 to 0th power all the way to 2 to 7th power. 7th power, 1% here, you still get 1% in yourself, but MSB, the importance, the weight of MSB is 128 times higher than LSB. So 1% here means what? 1% for MSB means 128% for LSB. Got it? 1% for myself. The variation for myself is only 1%, but I am more than 100 times important than you. Okay? So from your viewpoint, you are only LSB, I'm MSB. I'm 128 more times more important than you. So 1% for myself means 128% for you. It doesn't make sense because it's much larger than 50%, right? So how to make it? You say, hey, for example, I reduce my area and provide you more area. Are you happy? Yeah. Why? Because I reduce my area, it means I will get more variation, maybe from 1% to 4%. Who cares? I'm LSB. Overall, we can tolerate 50% in error. Okay? So, for myself, LSB 1% means too good to be true, too less. I had to better sacrifice my area to MSB. Because the more area for MSB, the less variation here. Got it? That is the idea. So, for LSB, we had better reduce the chip area. And for the area we saved from MSB, we can allocate to MSB. In brief, we have larger area for MSB, smaller area for LSB, and overall, the error will be reduced. Okay, and yeah, there's some kind of K means the area ratio between 2R and 1R. In practice, I still think 2 will be good enough. Okay, but how about M? It means from LSB to MSB, for each higher bit, how larger the area will be. Okay, it means what? Okay, let's go back to here. M means for these 2R and the next higher bit, your area divided my area, it means M. Okay? For example, if M equals 2, it means what? Your area is 2 times higher than mine. Okay? That's it. That's the idea. You can see where is the maximum? Around here. We have studied that. I have no idea. The square root of, somebody do something. The square root of 3.2. Yeah, we derive it. Yeah, anyway, it's very close to 1.8. Okay, in practice. Yeah, but anyway, it is still close to 2. In the past, there was the paper. It said, not by derivation, by simulation, it says 1.7 is the best. But for ours, 1.789 or something, very close to 1.8 is 1.7. Why? Because in the past, they have normal distribution. Okay, but we use log normal distribution. Yeah, that is more complicated, but yeah, even more practical. Okay. Anyway, that is what I recommend you. Okay. The more important, you need to allocate more area for them. Okay, that's it. Yeah. Anyway, so this is what I need to warn you. Oh, sorry. If you allocate the same area for each bit, it means M equals 1, not here, okay? You can see M equals 1. 1.789. Yeah, that is the square root of 3.2. Yeah, we derive it. Anyway, you can see in practice, if you have M equals 1, it means everybody get the same area. From MSB to LSB. Okay. For the simulation, the yield to my memory, okay, will be less than 70%. So the yield difference should be more than 30%. For only 8 bits. For higher bit, you will get even worse for the yield. Okay? Again, to allocate the same area, for MSB to LSB is really a stupid idea. Don't do anything like this in your future. Don't do it. Okay? The more importance, had better get more area. That is the very easy idea to enhance the yield. Okay, so finally, yeah, before the short break, I need to get my coffee. But anyway, if you do the same silly things as your seniors in the past, I mean, allocate the same area to MSB all the way to LSB, I promise you, for only 8 bits, you will lose about 30% of the yield. For more bits, you need to lose more. Okay, maybe more than 50% or 60%. It doesn't make any sense for you. All right? So this is what my conclusion. You can see, never mind how to make it. So my recommendation is this. Look, the red one. Why? Because that is the easiest for you to do your layout. M and the K both are 2. Yeah, it means what? The area from this to that, it will be doubled. From this to that, also be doubled. Okay? That is for 2R. And how about 1R? The same. This 1R and that 1R, it will be doubled. The area will be doubled. That is for M. And how about K? K is the area you allocate for your own, the same bit. Okay? The same bit. I have 2R and 1R. So the area for 2R and the area for 1R, that is K, is still 2. Okay? It means what? 2R. 2, 1R connected in series. That is what I mean. K equals 2. Okay? So finally, even though this is not the best, no, but it is the easiest for you to do your layout. M and K are both 2. That is the easiest case. Okay? And how much in difference? Not much. You can see. For the maximum, in theory, all right? What is the difference? About 1%. All right, okay? And the CD old case for 8-bit is already 30% in difference. But this one, the difference between the red one and the optimum one, what is the color? Light blue or something. Anyway, the difference is only 1 bit for 12 bits. Who cares? Okay, 1%. Sorry, 1% in difference means nothing. Okay, for after fabrication. Okay, so that is what I recommend all of you to follow this idea. Briefly, my conclusion before the break is the more importance, the more area. That's it. My recommendation is you allocate the chip area according to their importance. What do I mean? To their weight. The more weight, 比重越高, the more area. Okay? So let's go back here. Easy to death. Okay? What is my importance according to you? Hey, I am 1 bit higher. So my importance is 2 times than you. Right? Right? So I need to allocate 2 times more area than you. That's it. My simple recommendation for you goodness in the future. Allocate the chip area according to their weight, according to their importance. The more importance, the more weight, means proportionally more area. If I am 10 times I'm 10 times large, 10 times more important than you. It means if my weight is 10 times more than you, then I need to allocate 10 times more area. That's it, proportionally. 听好不好？听好不好？我的比重、我的权重，还有我的那个叫什么东西呀、或者是我的那个重要性，我比你重要多少倍，我的权重比你高多少倍，我的面积就是要比你大多少倍。Yeah, that is my very easy to understand recommendation for all of you. And it will make your future totally different from the others because beyond the class, till now nobody knows the secret. Okay, we try to publish the paper. Yeah, after revision we will submit. Anyway, for all the others, maybe next year they will see, oh, they did everything wrong in the past. Okay, but you are in the class, you know the idea in advance than all of them. Okay, all right, we can have a short break right now. I need to get my coffee.